For the next week or so, we're going to look at trying to get some realism in the displays that we or should now know how to construct and how to view. If you look at the one examples we've had, all of the examples have been using flat polygons, and I've used that cube, and our ability to sort of see its three-dimensionality was based on really it having very flat surfaces, and then I could color each surface with a constant color, or perhaps I would interpolate between the colors of the vertices. But that really doesn't work very well for getting anything really realistic, or if you have any kind of a curved surface. So what we want to do is really worry about how we, what's called shade objects, get little variations in color displayed for the object, so they really look like they're three-dimensional. I'll give you the classic example of trying to look at a sphere in a minute. And so to do that, we're going to introduce some light material interactions, both from a physical basis and then look at a computer model, because we need to be able to do these calculations very quickly that will give us something that's fairly close to the physical model for many circumstances. And at the end of this, we'll be building a model called the Phong model, which was built into the fixed function pipeline. Actually, is a modification of that called the Blin-Phong model that we'll fill in the next lecture. But today, we just want to give you what the ideas of the model are and the basic components of it. But let's start at the beginning and say, look what happens if we try and shade a sphere and just try and give it colors, or give it one color and say, okay, well, I can recursively generate a sphere. It's something we'll do a little bit later in this chapter. Or suppose I try and generate a sphere with longitude and latitude and get little polygons that I'll color. But if I use a solid color, it doesn't look like a sphere. It just looks like a circle, all because of every polygon is coming out the same way. But what I really want is to be able to see these gradations of shading. This isn't the greatest example here, but you see some of the thing. It looks a little more spherical because we see the colors changing a little bit. This part is starting to be in shadow a bit. This part looks like the light is coming from here. And so it really looks like a three-dimensional object. And that comes not from the underlying model, but it comes from how we decide to render it and how we decide to assign color. So instead of just assigning a color to be some RGB value, what we're going to do now is derive those colors through a model that uses the interaction between light and the materials that we want to model that surface with. Okay, so what do we need to be able to do that? The reason we said it, as we just said, is again that there's interactions that go on between the light that strikes the surface and the materials that comprise that surface. And what we need to do to model that is to consider a bunch of things. First, obviously, where the light sources are. We need also to worry about, obviously, again, what the properties of the materials are. And now what that means for the materials is that, they'll absorb some light and they'll reflect or scatter other parts of that light. So we want to know how much of the light they absorb. Darker materials will absorb more light, but we also want to look at their properties in color, because they'll react differently for different incoming colors. So, for example, if you have something lit, if you have, say, a red ball and it's lit by a white light, why does it appear red? Well, it appears red because that material absorbs the light frequencies outside of the red range and reflects the light that's in the red range. So we need to model that. We also need to model a little bit more complex interaction, which says, well, yeah, some light is absorbed and some is reflected, but how is it reflected? Is it reflected in all directions, that's scattered in all directions, or is it reflected in just one direction as would a mirror? So we need to look at that. So we need light properties, where the light is, how the light is distributed, what color the light is. We need the material properties. We need to know where the viewer is, because if if we have a very shiny surface, if you're looking at, say, the reflection of light in somebody's glasses, or you're looking in a mirror, it depends exactly where that viewer is. You may see the reflection of light in someone's glasses, but some person next to you may not. So it's very dependent for certain kinds of scattering on where the viewer is located. And finally, we need to know what properties of the surface, what its curvature is locally, what its orientation is. And that's what you see here. Here we have a sphere, and the properties of the sphere are the same all over. We have a light source somewhere, and why does it look different over here than it looks over here? Well, that's because the surface has a different orientation relative at different points relative to the viewer and relative to the light source, so we have to build that in. So these four elements should be part of any model that we want to build up. Okay, so now let's go back and look a little bit at this problem of light material interactions and see how we can build up models. And we're going to look at different categories of it, because building up one physical model that covers everything is going to lead to a very nice physical model, but not something we can use for computation. So here in this whole presentation, you're going to see a lot of very clever tricks to come close to physical reality, but still have something that's computable. Okay, so let's look at the following. Here you have two surfaces, and let's assume they're different colors. And you have some light, here's our viewer, and you have some light striking one, and it's scattered. It doesn't go all in one direction. This might be a wall in a room that would scatter light close to equally in all directions. And here's another surface that might also do that, but it's different color, so the scattered light is going to be a different color from the scattered light here. Now, look at surface A. Some of the incoming light is going to be absorbed by the material, and some of it is going to be scattered, and that's going to have a frequency-dependent property. Likewise, the same thing is going to happen at B. But that isn't the end of the process. If you can do a model like this, but if you do a model like this, it's not quite modeling the physical reality, because what's happening in the physical world is the light that strikes B and is reflected down, some of it is going to come and hit A, and likewise some of the light that's reflected from A is going to be scattered and strike B. Well, from B's point of view, light that comes from this light source and light that comes from A are just incoming light. They may have different frequencies and strike B at different angles, but from B's point of view, it's just light coming in, and therefore this scattered light from A should also be partially absorbed in our model, and some of it will be reflected and some of it will be reflected back to A. Likewise, light from B will hit A, some of it, and be scattered, and some of that will come back and hit B again. So it's this recursive process that goes on, and you can see that. One way to see that is if you can find an intersection in a room between, say, this would be ideal, between a red wall and a white wall, you would notice what is called the bleeding of colors. Right at that corner, some of the red would bleed onto the white wall, and on that corner, the red wall would be a little more towards the pink because some of that white light got mixed in with the red that was coming off of that surface, and that's what gives you a very real looking flavor, and also makes it a little hard to model and carry out very quickly. But if you want to look at that and get an equation for doing that, one way is if you sort of look at the limit of this kind of recursive process that goes, some of this hits here, some of it comes back, then it goes back and forth. The limit of that mathematically is going to give you an integral equation, and that equation we'll look at a little bit more perhaps later in the course, but it's a beautifully simple looking equation, and fundamentally it's an energy balance that says, well, look, all this light coming in is really energy, and we can do an energy balance and write it out in this equation, or you can build up to this equation recursively. But regardless of that, you have this integral equation which really you cannot solve in any kind of analytical way except for special cases, ray tracing being one of the special cases. And so this is, but it's global. This equation is global because it involves all of the objects in the scene, all the light sources in the scene, and all of these multiple interactions, which is nice, but global is kind of scary when you're primarily working with pipeline renderers. We'll look a little bit here, a little bit more at ray tracing and see why ray tracing is a special case. Let me come back over here. Ray tracing is a special case, and we'll come back to reflection a little later in this lecture. But light doesn't get scattered all over. If this is really like a mirror, then light will only come off in one direction. Remember the old rule, angle of incidence equals angle of reflection. And so I don't have to worry about all of these scattered rays. I just have to worry about this one. And that's possible to do, to trace, and that's why ray tracing is a viable alternative to what we've been doing with our pipeline rendering. But as we'll see in this discussion, it's really good for mirrors, but it's not so great for more realistic surfaces that you find in the real world that do scatter light in all kinds of directions. And now we want to focus on those kinds of materials in our renderings. Okay, so the rendering equation exists. You really can't solve it in special cases, but it's nice to know that it's well understood what's going on physically. Now let's look at it from a slightly different perspective and just emphasize what we've talked about before, that this whole thing is kind of a global phenomena, that if you really want to follow rays of light into the eye, because remember when we did our model in the first place, we said, well, the only ones that matter are the ones that come into the eye. These rays, like this one, goes off to infinity. I don't care about that. I'm not going to see the result of that. Or if it bounces off the top of this cube and goes off to infinity, I'm not going to see that. So what I'm going to see is perhaps directly light coming from the source. I may see just a very straightforward bounce like I see off of this cylinder, or I might see multiple bounces, like here it bounces off the cylinder, then bounces off, well, this one's not coming at me, but bounces off the cylinder and then bounces off the cube and then goes off to infinity. But potentially something could bounce off the cylinder, and depending on the orientation here, and then I'd see that too. Then you'd have more complex effects where if this was a translucent sphere, like a glass ball of some sort, some light would be reflected back to me off the surface. Some of it would go and be transmitted through and then come out the other side. This ray might go off to infinity, but it also might bounce off something and come back into my eye, which obviously complicates things a bit. But these are all kind of global effects, because to compute pretty much everything I just talked about, you need to have all the objects around to do that, and you can't just independently say, I'm going to process this cylinder and be done with it, and then now I'm going to process this cube and I'll be done with that. Can't do that for the really physically kind of based renderings. Okay, so this is just saying what I just covered, that it's kind of incompatible. It's correct, but it's kind of incompatible with a pipeline model, which is working not even an object at a time, but a polygon at a time. So we call that a local versus a global rendering. Now, historically, in computer graphics, because what we're able to do was much more limited than what we can do now, people were generally happy to say, look, if it looks kind of okay, we'll accept that, and it looks basically right. I don't care about the exact physics. And there were a lot of techniques that we've talked about. Like when we talked about shadows, we saw some techniques for approximating global things. Shadows were global. That worked pretty well. We're tending to get away from that because GPUs are so powerful, and we can process so much geometry and do complex calculations inside of the GPU that have enormous floating point rates, that we're doing much more things that really have to be based on the physics. And even the other place where the physics comes in, we'll talk about more later, is the actual modeling of the objects, where we're modeling them in a much more physically realistic kind of way. So, for example, if you were trying to model oceans and spray and waves like you see in the movies all the time. The original models were pretty simple because that was the best we could do. Now, when you look at what's going on in animations that you see and special effects you see in movies, those people are really modeling the real physics. They actually hire physicists and engineers to build these models because we can carry them out now on present computers. So this is also true at the level we're working at, where we're saying, oh, gee, what happens when light and interacts with the material at the surface? We can start talking about more complex models. Although, for this week, we're going to be talking about a fairly basic one. Okay, so let's look at light material interaction. Let's not worry about global things for now and just say, here we have light that's striking an object. We said that's partly, some of it's reflected, some of it's absorbed. The reflected part is called scattered because it can go in all directions depending on the material. So the amount that's reflected is going to give us the color that we see and how bright that color is, or the shade that we see. And so if we see something as appearing red, it's probably red because if it was what we call a red surface, if we hit it with white light, then only the red would be emitted. Of course, it could be a white surface being illuminated by red light, and we might see something similar. But basically, let's worry about how we model the light sources, how we model the materials. Then we can talk about how we combine those together into getting a model that we can apply. Also, the final point here, we'll see more examples of this in a minute, is that how light is scattered is really a measure of how smooth that surface is locally. If the surface is rough, it's going to scatter light in all directions. If the surface is smooth, it's going to act more like a mirror. So and in a way that's independent of how much is absorbed and what colors are reflected. If you could have something that's fairly that absorbs most of the light, kind of like, say, like a black mirror that absorbs most of the light, but still the part that it reflects is still reflected as if it were a mirror because it was a smooth surface that absorbed a very high percentage of the incoming light. Okay, so we're going to break this up in two parts. First, I'm going to look a little at light sources, and then we'll come back and look at the materials. Okay, so here's a light source, and here's an argument about why working with real light sources is difficult, and why we tend to use some models to approximate them. So here's a simple light source. If I want to know what this contributes to the surface, well, certainly I could take any points on this light bulb, and I could now draw the line, the directed line segment to the point I want to say what color do I put at this point. Now, a couple of things are going to happen here. One is that these distances could be different depending on how far that light is from the surface. It can make a big difference. And the angles that it strikes this surface with are different. So in principle, whatever my model is for what happens at this point from the light coming in at this angle at some frequency, I'm going to, in principle, have to apply that model at every point on the surface of this bulb, which can have a very complicated shape. Now, obviously, that's something we're not going to be able to do very well, even if we're not worried about doing things in real time. This is a pretty tough calculation to do. And in fact, if I want to make it more realistic, I could say, oh yeah, well, this light bulb has a surface, and it's also reflecting light that comes and hits it, and some of that light that hits it might come back and hit this surface over here. So to do something truly realistic, you could see is hard. But the most problem I have is that any kind of a distributed source is going to propose a difficulty for us using a lighting model. So we work with things that are really simple. Well, what kind of simple things? Well, the simplest things are point sources. Point sources is infinitely small. It has a position, it has no size, and we can assign a color to it, where what I mean here is that some distribution of frequencies with different energies at each frequency can be coming out of light at that point equally in all directions. Now, what we're going to do is, because we're so tied into an RGB model, because we as humans, thinking going back to the first week of class when we talked about the visual system, we see three primary colors, and because so this model means that we really can use just three primary colors for our light sources. And we'll wind up doing that. We'll say that, okay, what's a point source? A point source has a location and it has an RGB components. The distance, though, from that source to the object will matter, because we know that the light intensity will go down as 1 over the distance squared from the light source. We also can argue, and this can really increase efficiency, is if the light source is really relatively far away from us, like the sun, then we could say that the rays from that point source are coming at us in parallel, and when we render polygons with lighting and shading, we can actually use that fact to simplify the calculations. Okay, the other kind of light source that we can get from that is a spotlight, and that's really easy to do, because we say start with a point source, and let's just consider, instead of 360 degrees going around it, what we'll do is just consider a certain solid angle coming out of that, and everything else is going to be 0, and that gives us a spotlight. So a spotlight will be like a point source. It'll have a location, because we'll need to at times worry about the distance from the light source to the surface. It will have RGB components that give us the color of that source. And we can also do things like say, well, a real spotlight doesn't distribute light equally across its angle. It actually is strongest in the center and tapers off to the sides. We could build that in, as that's in the notes fairly simply. But basically, a spotlight isn't much more difficult to consider than a point source. Now, what about distributed sources? Well, we just said distributed sources are really a problem. What about modeling distributed sources with a bunch of point sources? That's possible. We do that a lot. Also, we do a lot of placing them carefully, just as they would do in a movie. In a movie, the lighting people will put little lights just exactly where they want to get the right light on this person's face, and none of it striking another person. We can do that in computer graphics. But as we'll see, you have to do the lighting calculation for each light source. You don't get any benefit when you go from 2 to 3 to 4 other than what it looks like. If you're going to have 4 light sources, it's going to take you 4 times as much work as computing for 1 light source. So we can have a lot of point sources, but it's a problem computationally if we have too many. So one of the things we do is say, well, what's the result of having distributed sources in the real world? So if you look at the lights you would see in a kitchen or in a classroom, you would have these plastic, usually, covers on the lights, which would be diffusers. The idea of the diffuser is to scatter the light all over the place, and when you combine that with that light reflecting off various walls in the room, you wind up, at least approximately, with the same amount of light everywhere in the scene. And actually, you would locate your lights and build the size of the diffusers, so you would get an equal amount of light everywhere in the room. That's called ambient light, and if I have ambient light, then I don't have to worry about where the location of any source is, or any directionality. All I need to know is the strength and the color of that ambient light. And what we generally do then is use a combination of point sources with ambient light to get close to what we want to see. And generally, the other problem with point sources is that they tend, if you look at the resulting light, they tend to give you very sharp transitions. If you look at a point source and a shadow from a point source, ideally that would be exact. Either you would be in shadow or you wouldn't be in shadow. For a distributed source, any kind of real source in the real world, that wouldn't happen. You'd have a transition from a full shadow to no shadow. There would be, you call that the umbra and the penumbra, the little region where you have transition. ambient light can soften things up and get rid of a lot of the harshness that you would see by just having a point source in the scene. Okay, so light sources, pretty simple, the ones we're going to be able to handle. What about surfaces? Well, we're going to go somewhere between having an ideal smooth surface that will reflect in exactly this perfect direction to having an ideal, what's called an ideal diffuse or Lambertian surface that scatters light equally in all directions. And we're going to be somewhere between this. But again, some of the way we've used these models to get something that looks okay but doesn't require too much calculation is to use sort of both of these ideas, even though they're not physically what's really there. We have one light source that's doing something in one material, but if I use a part of it I model with this and part of it I model with this, I can get something that's computationally efficient and comes close to what's physically going on. Now, the basic model that people have used, I think early 70s, was the Fong model. He was a graduate student at Utah and came up with this model that said, he wanted to be close to physical reality, but be reasonably efficient. So he said, let's model what goes on, our lighting calculation, with three different parts. A diffuse component, that's the part that corresponds to light scattering and equally in all directions. A specular component, which is like a mirror or a very shiny metal surface, which concentrates light in a narrow angle, the limit being a mirror, and then an ambient component, which gives us equal light in every place in the scene. Now, to do that computation, he used four vectors. Okay, one was at first. Let's consider a single source. So there was a vector from a point on the object, because there might be a different shade computed at every point. So we have a point P, and we can look at these four vectors as emerging from that point. There's a vector from that point towards the point source. Remember, we're dealing with point sources. A vector to the viewer. These are obviously the two crucial ones. But our models are going to use two more vectors. One is the normal, which is the normal to the surface at that point. So if we assume that just in a very small area around P, the surface could be modeled by a little flat polygon, that polygon has a normal to it. So we have a pretty well-defined concept of the normal at every point in at least a reasonably smooth surface. And we're also, in order to cover this specular term, we're going to want to talk about the angle of a perfect reflector, R, but that will have the equation in the next slide, is derived from knowing where the light is, what the normal is, and where the viewer is. That'll not where the viewer is, where the normal is and where the light is coming from. That'll give us the angle of a perfect reflector. Okay, so let's look at that one first, and then we'll look at the other components. Okay, so here's a little derivation. It's in the notes. It's pretty simple to do. So the normal, as we said, is if you put a little polygon down at a point, you can talk about its normal at the surface. So we should be able to have that angle, or we define it in our code. The angle of incidence is the angle between that normal and the incoming light. Now, the basic rule that you get in high school is the angle of incidence is equal to the angle of reflection. Well, that's true, but it's not enough, because I can rotate this R all over the place and still have the angle between the normal and R to be exactly the same as the angle between the light and the normal. So it's just not complete. The complete statement is that in 3 dimensions, these 3 vectors must lie on the same plane. And if I combine that, then what that says is 2 things. I'll tell you in words what the derivation is. These 2 angles have to be the same, but therefore the cosines of these angles have to be the same. Cosines are given by the dot product. So if I normalize everything, and by the way, when you're doing lighting calculations, you almost always want to normalize all these vectors to have unit length 1 first, because you're going to wind up having to normalize them later, so as part of the process, generally you'll normalize these to unit length immediately. So if these have unit length, then the cosine of this angle is just L dot n. And likewise, if r has unit length, then you have that's equal to the cosine here is equal to the cosine here. So you have L dot n equals n dot r. So that's one equation that's saying the angle of incidence equals the angle of reflection. If they're coplanar, that says that r is a linear combination. It's alpha times L times I, where the light is L, and plus beta times n. It's a linear combination of these two vectors, which is a valid. This is valid operation from the vector spaces we talked about. Those give you two equations in two unknowns, alpha and beta, and you can solve them to get r and also ensure that r is unit length, and this is what you get, which is the standard equation for the reflected vector in terms of the normal at that point and where the light source is. And by the way, remember there was a function in GLSL that does this. If you give me two vectors, there's a function called reflect that will return this vector for you if you do your lighting and shading calculations in GLSL and in the shaders. Okay, so there's the ideal reflector. We'll need that for the specular term. Now let's first look at the diffuse term. Okay, so a perfectly diffuse reflector. It's kind of what you get with matte paint that you use on walls that doesn't have any shiny spots. It scatters light equally in all directions. Now that doesn't mean that the amount of light, the brightness you see is always the same. This says that if it scatters it equally in all directions, it doesn't matter where the viewer is because every viewer looking at that surface will see the same thing. However, the amount of light reflected is dependent on how high in the sort of the artificial sky the light is. That says, so if the light is striking it perpendicularly, if you think about it on flat, think about the sun and you're standing out there, and when the sun is right overhead, it's at its brightest, but as the sun goes down, it gets less and less light. That's because what you're seeing is only the vertical component of the incoming light, and that's proportional to the cosine of the angle between the light and that normal, until when that sun gets down to 90 degrees and it's setting, there's no more light at all. So that's what ideal Lambertian surface would do this perfectly. And since it's dependent on the cosine, here's where again the computational niceness of this model comes in, is it depends on the cosine of that angle. But again, if the vectors are normalized, the cosine is just L dot n. So it says, okay, that this diffuse component in the Phong model is some constant times L dot n, where the constant has to do with how much of that component is absorbed and how much is reflected. So we would see something like, 0.5 L dot n would mean that half of the light was absorbed and half it was reflected. But in fact, we want to do that 3 times, because if we're modeling the light as having a separate red, green, and blue components, then we have to model the surface as having red, green, and blue coefficients that determine how much light is being absorbed and reflected for those incoming red, green, and blue components. So there are three coefficients, Kr, Kb, and Kg, that show how much is reflected. So there's the simplest model. It's only made more complex, as we'll see later, because I haven't included a distance term here. So I might, depending on whether the lights are really far away from me or not, I might want to divide this by a distance term. Obviously, if we're talking about sunlight, it really doesn't matter how much further or closer I am to the sun than you are if you're in the same scene. But if we're talking about modeling this kind of a component, say from a lamp in a room, then obviously the distance you are from the lamp and I am from the lamp is going to lead to different values here. But I'm leaving the distance term out for now because all that is going to do is divide this by some value. Okay, so that's the Lambertian surface. That's the diffuse term in the model. The ambient term is just a constant term in there. And the third term is this specular term. And that's, here you're seeing a blue ball. This would be the diffuse terms out here. You notice this is showing what we were just talking about, that if the specular term is showing that this light source is probably up over my right shoulder when I'm looking at this, and that further away from that point where you have the brightest reflection, the diffuse term is getting smaller and smaller because this surface is not pointing towards a light source at all. Here it is pointing more and more towards the light source as we go up. Now, smooth surfaces are going to show these specular highlights, and notice here that this is very typical. A good example of this that people always use is an apple. If you have a red apple and it's very shiny, you're going to see a white highlight on that apple. Why is that highlight there white when the apple is red? Well, the answer is that shiny surfaces are like mirrors. And what mirrors do is, what do you see in the mirror? You see the environment. And so that little highlight spot, or the specular highlight, is actually the reflection of the light source or something bright in the environment that's reflecting off here and back into your eye. So another reason for, even though we don't want to model that reflection because that would be because that would be a global calculation. If I know where the specular term is going to be its maximum, I can give it a different color, which is what we've done over here. Okay, so the specular reflection gets modeled somewhat like this. It says, okay, there's the ideal reflection angle, which we just derived, and if I'm along that ideal reflection angle, I'm going to see the most of that incoming specular term is going to be at the maximum over here. And the further away I am, it's going to go down. And so the angle between the viewer, and it's going to be different for every viewer, the angle between the viewer, phi, and the reflection angle is phi, and it's going to depend on that. And the bigger it is, the smaller the amount of specular light that I'm going to see. Well, what's a function that does that? Well, a function that does that is in fact the cosine. The cosine is maximum when phi is 0, and it goes down to 0 when you get to 90 degrees. And notice also it's symmetric around this. And so when you go in this direction, you get the same results to when you go 90 degrees over here. So the model that Fang was proposed, and this model would be for each color. So I'd have this for the red component, the green component, the blue component. The reflected intensity would be, there would be an absorption component for an absorption constant for each component. The intensity of the incoming light at that for that component, and then this cosine term, which would be dependent on the dot product of V and R. Now that's great, except it doesn't distinguish between surfaces that are really shiny, like a mirror or some highly polished metal, or surfaces that have this specular highlight, but it's more spread out and more diffuse, like you would see if it was a metal surface, curved surface that was a little dull, not all polished. So what Fang proposed is, well, why don't I put a constant in here, alpha, which is called the shininess coefficient. And the higher that shininess coefficient, the more concentrated the angle will be. We'll see that in this final slide. That here's cosine this is cosine of phi just for alpha equals 1. So this is the cosine between 90 and minus 90 degrees. Now what happens when I raise this to a power? Well, because the cosine is between 0 and 1, all the values other than 0 and 1 get reduced. You have a fraction, it keeps getting smaller and smaller as I raise it to higher and higher powers, but 1 to any power is 1 and 0 stays as 0, so that as I put higher and higher values of alpha in here, I get a narrower and narrower little focus, so I'm getting to be more and more like a mirror. So if you use this model, values like between say 100 and 200 might correspond to very shiny metals, and values between 5 and 10 might give you a surface that has a little bit of a specular highlight, like something made out of plastic. So these are the three components we want to do. We'll see a variant of this which gives us which is a little more computationally efficient, which is gives us the modified Phong or the Blin-Phong model. But the basic concepts are exactly the same, and we'll derive the equations and start using them in the next couple of lectures.